Dominic, talking about electrons.
Yeah, so I'm excited to tell you about this result, which is basically about getting the best possible codes in 3D. We've had some nice introduction to what the restrictions are already, but I'll be telling you about how to saturate that. And yes, I recently moved from University of Sydney to IBM, but this talk is about work I did at the University of Sydney with Noidem Baspan, who's in the audience, so you can also ask him questions if you're around later this week. Oh yeah, and before I start, I'm not really going to talk about this much during the talk, but I need to mention there is like an earlier work that went in archive, which has a related result that is in some ways better, in some ways worse, by Portnoy, which is very impressive, hard to understand. Like, I don't understand it. It uses a whole bunch of, complicated theorems. And then there's a follow-up work that maybe is a bit more similar to what we did, but again, I don't understand fully. Me and Noidem are humble fellows. We don't, really use any kind of crazy theorems in this result, except for relying on the existence of good LDPC codes and surface code tricks. So let me tell you about how that works. Yeah, so if you're going to fall asleep, or if I get overwhelmed by comments and I don't get through any more slides, this is the only thing you need to take away from the talk, that we have, in some sense, the best possible codes in three-dimensional space with spatial locality. And the whole construction is based on the existence of good LDPC codes and the existence of the surface code, and then some tricks to glue them together. Okay, cool. A little bit of motivation. So I think we've had some nice intros today already, talking about how connectivity restricts you. So we have this nice result that they're sort of, even with low density, there are these good codes, which are what we really want, but they require like a lot of connectivity. That's very daunting. With sort of minimal connectivity, which we kind of really need to go to 2 dimensions for code families to be any good with local couplings, we have this really nice example, the surface code. And you really can't do much better than this if you're going to stick to 2-dimensional locality. Okay, but there's this big chasm in between, and you could just try to shoot for going directly here. I think it's interesting to ask what's closer to this side, and so that's this work. Saying one step you could make is by having something more like 3-dimensional locality or coupled 2D chips in quite a restricted way. And then you can already improve the code parameters quite a lot. And in some sense, it's the best you can possibly do with the code family with 3D locality. Okay. And the way that the talk is sort of structured is that I'm going to just sort of reiterate that good CSS LDPC codes exist. But they're going to kind of be a black box for me. I'm not going to go into the construction of them. And then I'm going to mention, these BPT bounds and related things, which people have already introduced, so I'll go quickly on that, which the surface code saturates in 2D. And then I'm going to show you how to put together the good LDPC codes with the surface code and make this family that we are going to use to saturate the bounds in 3 dimensions. Cool. So this is my picture, the tannograph. We've already had this background, so I'll go quickly here. I'm going to use blue consistently, I hope, in the talk to mean sort of X, like logical operators and checks. So here we have some checks in the Steam code. These, this connectivity denotes where the X operators go in our products that give us the local checks on the qubits. The qubits for me are also around, so whoever had that convention, I agree. And then the red boxes are going to be our Z checks. Cool. This defines a code space, which is the +1 eigenspace of all these terms, which mutually commute, so this makes sense. And this is isomorphic to some number of qubit algebras tensor producted together. Okay, and this is going to be called K. It's going to be K qubits stored in our N qubit physical space. Good. And here, LDPC just means that this tannograph is sparse, so low degree, going both ways. And I'm going to use this notation, this sort of standard notation, where you have NKD, the number of physical qubits, number of logical qubits you're encoding there, and the distance, the lowest weight operator you can apply that will not be in the stabilizer group, but will implement a non-trivial transformation in the logical space. And in this notation, a little example here, the Steam code is a 713 code. It's easy to see why you have 1 encoded qubit, because you have sort of 6 checks on 7 qubits. Seeing the distance is a little bit more tricky. Okay, and now here's the first point. So In this family of sort of sparse tanagraph quantum LDPC codes, we have these good codes, and there's a whole bunch of work, so my references are not going to be the most exhaustive. But essentially, the first work to prove this result, I understand, is the Panteleev-Kalichev paper. And there's a whole bunch of cool work before and after. Maybe ask someone else about that. There's plenty of people here who know. Okay. But taking kind of a left turn, these are good codes. They're on these kind of very expanding graphs. What if we're stuck in some finite dimension? So this is where topological codes live. They have checks that are kind of local on the lattice, because we might imagine we have like superconducting chips. It's really hard to make things talk to each other that are far apart. Maybe there'll be some great experimental breakthrough from IBM and we can do that. But maybe we can't. And if we're stuck in some architecture where we can't, it's nice to think about what you can still achieve there. And so maybe the first thing maybe it's obvious to us in retrospect, but it's not super obvious at first, is that just with local checks, we can detect and correct all local errors. And so this is sort of nice because it's motivated by imagining that the connectivity in our device that lets us do these sort of measurements of the checks is also going to be what the errors will naturally want to follow. And so with sort of the same natural connectivity, we can catch the errors that will naturally occur. So that's a very nice thing about this family of codes. And then there's really nice connections to physics. So these things these code spaces naturally match the ground spaces of some local Hamiltonians, which lets you understand their properties in terms of some physics we know, and relate the properties of the codes back to some interesting physical systems, which are of interest to people in the physics department, for example. All right, so here we got to the BPT slide. We've already kind of seen these bounds, I think. Here's my version of them. The only difference is I like to think of things as being some square or rectangular prisms. So instead of writing everything in terms of n, I'm going to write it in terms of lengths. So here, and this is a 2D picture, we have like an L by L kind of grid of qubits with some finite density. And the BPT bound is going to say something that looks a little bit complicated. It's easier to kind of strip out this part that's telling you about the distance, which tells you that the distance basically has to scale at most like a codimension 1 object. So in my 2-dimensional picture, it's got to live on like a 1-dimensional sort of line. And the way to understand this is basically in these codes, like everything that's local is correctable. And so you just sort of grow the correctable region to the largest possible size you can without kind of making a logical error. And you cut that out, and then all your logical information has to be stored in the complement, or you could sort of clone and use this to push the support of where the logicals could possibly be. So that's the way to understand why the distance is codimension 1. Given that the distance is already sort of optimal, if you kind of think about how many logicals you could pack into the remaining space, given they can't overlap too much, you end up getting 1 more degree of dimension reduction. So in this picture here, there's all these pairs of like line-like logicals, and each one kind of takes up a linear amount of space, but the width you have is kind of constant. So if you try and pack these in, you can only get a constant amount in, and that's not like rigorous as hand wavy, but if you go through it, you can make various versions of this. One where you imagine you have optimal distance and plug it into BPT. The other has a nice bound where you have a different kind of assumption, and you prove that basically if your block is not broken up into a bunch of little disconnected chunks, the best scaling of number of qubits is codimension 2. Okay, and I'm going to focus on trying to saturate both of these at the same time rather than trade them off against each other. If you trade off having a good distance, you can kind of just break up whatever size you have into smaller pieces and get more encoded qubits with less protection. But the trick is we don't really need to solve that problem separately. Once you find some block that has the optimal K and D simultaneously, you can just take that and then consider a bunch of small copies of it and sort of tile them, and you'll saturate BPT for the whole range of the trade-offs. So I'm just going to focus on trying to simultaneously get the best scaling of D and K. Cool. And yes, as we've already seen today, the best you can do in 2 dimensions is kind of saturated by this surface code. But the best you can do in 3 dimensions, you can now have actually a growing number of encoded qubits with system size and a slightly better scaling of the distance. Cool, so how do you do that? Well, I got to start by telling you a bit about surface code. I'm going to consider the surface code with these kind of boundary conditions. So we have like 1 Z-like check per plaquette, including these boundary kind of truncated plaquettes, 1 X-like check per vertex, including these boundary sort of truncated vertices. And you can check these things always commute with each other because they come from some homology, some Z2 homology of a surface. What do the syndromes and logicals look like? Well, sorry, here I should say explicitly, I'm going to just like sort of switch to using this like red line notation to denote Z operators and blue line notation to denote X operators and not explicitly draw them all every time. So over here, you can check any red line through the primal lattice will commute with all the X checks, and so it's going to be a logical. And if it is not a sort of cycle ending at a boundary, if it goes between the two distinct boundaries, it won't be in the stabilizer group. And then you can find the dual X logical. It lives on the dual lattice. Again, it's like a closed string, and you see they overlap at one point, so they give you a logical algebra. You can check by counting, that's the only logical algebra in this code space. And so there you get your 1. And you can't reduce the distance beyond any lower than these two representatives, so that gives you the L. Okay, what about the syndromes? The syndromes are kind of point-like, living on the vertices or on the plaquettes. And we like to, if it's sort of physicsy talk, we like to call them E and M. So I'm calling the syndromes of the plaquette operators M and the syndromes of the vertex operators E. They pop up at the end of these sort of string-like operators. So they always sort of come in pairs in the bulk of this code. You can't make a single one. You can kind of make that a rigorous statement. But near the boundary, because you have different stabilizers there, you can make them alone. So near this boundary, you can make a single M. Near this boundary, you can make a single E. And that's what underlies having a logical qubit stored in this code. All right, so I want to introduce a little bit of terminology. Hopefully, if you don't like this, you can still follow. But I find it hard to think about these codes without using this. And it definitely inspired the construction. So in sort of physicsy terminology, we like to classify what possible boundaries are here by thinking about these syndromes as point-like excitations. And in 2 dimensions, point-like excitations can have some interesting braiding statistics. So in 3D, maybe if you did undergrad physics, you saw some argument that point-like excitations are always bosonic or fermionic, because if you bring one around the other, this is kind of a homologically trivial process. You can smoothly deform it to doing nothing. And this means that a full braid has to have a +1 sign, which leaves space for sort of fermions where you have a half braid giving you a -1. So then the full braid is +1. In 2D, there's no such restriction because these sort of particles braiding around each other give you like non-trivially linking world lines. And so essentially almost all bets are off. You get into some complicated theory of what's possible. Very general things are possible. These go under the name of anyons. In this surface code, you already get these point-like particles that end up being anyons. This just captures the fact that their string operators don't commute. So each one individually is like a boson. You can move it around, and it always commutes with its friends that are of the same type. But when you move them around each other, you get a -1. And then you can use this to solve what kind of boundaries there are. In this world, condensing just means you can make a single one of these particles or syndromes near that kind of boundary, whereas away from that boundary, there's going to be some conservation rule on them. So you can sort of change the rules at these boundaries. And the upshot is you can only have one kind of thing or only mutually sort of bosonic things condensing at the same boundary. Otherwise, you can't satisfy commutation of the stabilizer group. So you can't have E and M condensing on the same boundary. So here, your choice in the surface code is either E or M condensers, and those are the only choices. We'll see more complicated examples later on where there are more choices. Okay, and I'm going to go to 3D. That's what the work is about. And I'm going to need to drop a bunch of details so the pictures are readable. So here I have the full lattices kind of drawn in. But I'm going to abstract these lattices into some sort of 2-dimensional sheets that I'm going to be picturing in 3D like this. And my convention is going to be always that along these sort of bottom edges, I have E's condensing. So bottom and top edges, E's condensing. And these side edges are going to have M's condensing. So my X operators are going to run along my X-axis in my 3D coordinate system. My Z operators will run along the Z-axis. And I'm not going to mark that every time I have such a directed edge, it's going to be M condensing. You just have to remember that. Okay, good. And yeah, there's one extra slide I added because the last time we gave this talk, people got confused. I'm going to use this property a bunch, which is very familiar to anyone who does things with surface code, but it's like essentially the one trick we really need. And that is that if you have a surface code patch and you look at the product of all the local checks, say of Z type, it is equal to the product of the logical on the left and the right. So this is in the stabilizer group again, because these logicals are like Z2. But you get this nice isolated version of the logical on either side. And you can infer this purely from like local syndrome information. So we're going to use this property of the surface code to measure some logicals. Okay, so the motivation for the construction, like I promised you, was pretty down to earth. Besides using the good codes as a black box, our idea is basically, well, Neuden wanted to take the layers of surface code and just concatenate them with the good code. So here, again, I'm just drawing this kind of tangograph, except now things have changed a little bit. I'm doing a concatenated code. So instead of having these, this outer code sort of having single qubit X operators where it hits, it's now hitting surface code layers, and that's going to be replaced by a product of X logicals on the surface code layers. Similarly for the Z checks, you can check everything commutes again. And this gives you the code parameters you want. So you're like, great, until you think for like 1 second, and you realize that this thing has totally high weight checks, and they're totally non-local once you lay out your kind of good LDPC code in one dimension, where I've sort of stacked all the surface codes along one dimension. So you might need things that reach from one end to the other. And indeed, you actually need a lot of those things. And also where they're hitting the surface codes, they have weight L. So that's bad. Yeah, sad face. So the basic idea that we started with was just like, we should fix this by using lattice surgery. Lattice surgery is like sort of a name for using a bag of techniques for using the fact that you can infer these like high weight products of pairs of logicals through a bunch of local checks to turn high weight concatenated checks, if you like, into local checks. So here we have it like an example I'm drawing. Imagine you had like 2 encoded qubits on pair of surface codes, and you want to measure this ZZ logical operator on them. And this ZZ is on the different layers, not on the same layer. Okay. And this would be really high weight. And if you imagine they're very far away from each other in space and as part of some bigger code, they could be very non-local too. But this sort of lattice surgery idea lets you use another patch of surface code to infer them. And I'm going to draw this one in red. So the red patches are going to be like playing the role of my, they're going to be replacing these outer Z checks, if you like. And if you remember this red patch of surface code in the middle there, by just measuring all of the small stabilizers in that piece, I could infer the 2 logicals at its boundary. And so then there's like a little bit of hand waviness for now that I need to glue those in, because these logicals at the boundary here, they're part of a different code than these 2 decoupled layers. And so essentially if I can couple them in such that that logical is married to the logical Z on these 2 layers I started with, I win. And I have some local way of measuring this high weight non-local check. The reason it's also spatially local is because I can just put like some lattice scale and have many sites going between them. So I never have to measure anything very far apart in this sort of 3-dimensional grid metric. Okay, and I obviously pay some overhead here, but the point is it's not too bad. If the distance between them is scaling like the size of this code block already, it's going to not change the scaling of the code overall. And okay, so the way we like to think of, or the way I like to think of doing, describing these checks more generally is by what the string operators can do when they meet these checks when they're married together to meet the codes together. Okay, and so here, what we want this one to do is basically let like a pair of string operators that are of Z type annihilate. And so if you say that on the level of like a single string operator, you basically want this single string operator of Z type to be able to pass through this layer freely from either side. You also want that this ZZ does not like anti-commute with any Z string operators in a single layer. So the single Z string in the layer is allowed to pass through, but we want this ZZ to toss out like a single X logical operator, because now we are measuring ZZ logical on the 2 layers. And the way you do that is that basically you have some junction so that before like this M string could pass wander freely around in this layer, but now it hits this junction, there's a new stabilizer there, which detects that it hit and spits out some like error into the auxiliary surface code. And you have the same choice over here. Cool. So this is like a high-level description of this defect. And sorry, I'm going to use defect to just describe the place where they meet that looks different from the surface codes away from this line. So this is just like 1/2. It turns out you can divide this choice of this thing into 2 pieces, and they're identical. And then they're just joined by the surface code in between, which has got the regular kind of stabilizers of surface code. Oh yeah, and in this picture, okay, we still have some external kind of boundaries of the red layers. I didn't tell you what those were. It's pretty boring. On these like gray layers, I already had E condensing on the bottom and top, M condensing on the sides. And now I'm going to have these red layers, and they have bottom and top boundaries too. They'll be E condensing. And I'm going to have blue layers in a minute for the X checks. They'll have M condensing on the side. So they just kind of match what I picked for the these gray data layers already. That's the point of that. But I haven't described to you exactly how you pick this line defect and like what's the logic there. So these line defects, when we have a bunch of layers of surface code meeting, or more generally a bunch of layers of 2D codes meeting, there's a trick called the folding trick. That's in, well, first time I saw it was in a paper by Kataev and Kong. And it's a pretty silly thing. Essentially, you just think of a bunch of layers meeting at some line. You can just like, in your mind, rearrange them all to live on one side of the line. And then this is like some boundary of a stack of layers rather than being some more complicated junction. And so essentially by just describing these boundaries of many copies or different topological codes in 2D, you can describe all these junctions as well. And I told you before that these boundaries of surface code, so this is like just a number of copies of surface code, more generally that is given by some number of these like anion syndromes, where the subset has to have string operators that commute with each other and themselves, and you should have one per layer. So before we had a single E or a single M for one layer. If you have two layers, you could have a EE or EM, or you could have more complicated choices like E on both layers and M on both layers. Here I have 3 layers, and I need to pick the things that can be created there such that I get these rules I want for my logical that I'm going to measure. And so I'm kind of just compressing the description here a bit to say what's kind of being locally created at this vertex, at this junction, which you can view from the top as just a vertex. And it's going to be pairs of E and then 3 M's. So that's the choice. You might notice there's like a symmetry in the surface code where E and M are equivalent. And under this symmetry, this like junction maps to a different junction. And it turns out these 2 kinds of junctions are all I need in the construction. So these things both map like, they both describe some boundary of 3 copies of surface code, which you can sort of unfurl into being a tri-junction. And the 2 types I need are basically either M is not allowed through or E is not allowed through without spitting out another particle. Okay. Good. So how do I use these to describe a general a Z check or break down a general Z check that might pop up in my big code construction? I'm going to use this trick that might be familiar to people who like tensor networks or ZX calculus, where you can draw literally the tensor network for an X projection of a stabilizer like this. There's some plus tensor, which just is non-zero when the sum of the inputs is even. And there's some delta tensor that just is like non-zero when all the inputs match. You can write an X projection like this. And then you can use some rules of like tensor calculus to break up this big high degree plus tensor into a bunch of little degree 3 at max plus tensors. And we essentially take this approach to breaking up our many body check. So yeah, here's a good little picture. We take each little piece, which will involve one sort of delta tensor and one plus tensor in the stabilizer measurement. And we unfurl that along the line where we're going to try to measure these concatenated logicals. And then we replace each one of these with the surface code defect that I introduced in the previous slide. So each one of these tells you, 3 M's or 3 E's can condense, and then pairs of E's / M's depending on the plus or dot type. So now that once you've drawn that out, you have like the general description of what you should put on each of these lines for the layer code. Okay. And there's a similar version for X checks where everything runs in the X direction now, and you swap all the dots and pluses, but no new kind of pieces of information appear. And these are like, if you like, some kind of concatenated high weight checks that we've just done some weight reduction on using surface code tricks. Good. We're not quite done. You'll notice, yeah, now we have stuff running in the sort of YZ plane and the XY plane, and they're going to intersect along Y lines. So what do we put there? The most obvious choice, which we tried first, was nothing. Just have them pass through each other in a trivial way. That turns out to not work, and you need some kind of pairing structure. So because anytime you have an X and a Z check, they have to commute, they always overlap on an even number of qubits. And so we just pair these qubits up in like the most obvious way, according to the linear ordering we've picked. And we're going to need to use that structure to make this thing work. So here's an example of the 422 code, the tanagraph, and the pairing you get between the one X and one Z check. All right, and so here's what the layer code looks like. We haven't decided what we're putting on these green lines yet. Here's what like some error would look like if a sort of logical of the first layer tries to get applied. That's like a Z. This shouldn't be allowed, and sure enough, it gets picked up by this sort of X layer, X check layer, and makes a syndrome. The problem is because we've stuck in this Z layer, this guy now has a detour, and if we didn't put anything on this green line, it could just hop into this red kind of new layer and then just wander along that to the end, and we'd have this like bad logical. Like we don't want that. So let me just show that again. Basically, you can take a detour through the new layers we've added. And so the whole point of the green check is to stop this. It's to add some block back in that essentially participates in the X check where it crosses the Z layer, and the Z checks where they cross the X layers. Okay. And then on these non-green shaded parts, you just actually can put in the simple thing of the two layers passing through each other without talking. So let's go back to this example with this non-trivial choice of defect. And again, it's like just given by the lines we already introduced. And we just arrange them such that basically when an E tries to go through, when it's not meant to, it shoots out another E. It's that simple. So here, if we have this string operator that tries to take a naughty detour, it hits this new kind of defect we've introduced and spits out a syndrome as planned. Good. And so this is now everything you need for the one-dimensional lines. So we have like these Z checks, which we break up, the X checks, which we can break up, and then these intersections, which are either non-trivial or sort of trivial type. And now that once you put all that together, you've described the whole network, except for at the points where you have many things meeting together. But luckily, it turns out it's just like a bunch of grunt work to work out how to introduce stabilizers there. And these are stabilizers written as like a high-level string operators. So there's this many cases for points in the bulk, and you can just go through and make sure that you have enough stabilizers at each one. And there are a bunch of boundary cases, again, which you can work out. And then you can turn all of this high-level stuff back into a lattice model, if you like. So this is actually qubits on a lattice. This whole thing embeds onto like a cubic lattice or maybe a rectangular prism lattice with, I think, 2 qubits per edge at most. And the check weights end up being less than or equal to 6. Let me just show you one example. So we have these kind of red layers and blue layers and the black layers, which are the data layers. And then the checks here are just going to be a bunch of X checks that pop up. There's also Z checks, but there's no new Z checks occurring at this high degree vertex that didn't already occur on the individual layers, so I'm not drawing those. And those individual layers are surface code, so they'll be weight 4 at most. So here, the highest weight one you get is some kind of surface code check on the blue layer multiplied by a single Pauli operator on the red and on the black layers. And this is implementing some kind of one of those funny-looking string operator clusters from before. And then you have some other, 2 more terms, one from the red layer and one from mixing the black and red layer. So we work all these things out. It's quite a few cases, but they fit on one page. It's not too bad. And that's the model. Cool. So just a summary of the recipe, and I think I have time to talk about the parameters and the properties of the code a little bit. We take in some actually generic CSS code, which can be a good LDPC code. We make a data layer for each physical qubit. We put in like a Z check layer for each Z check of our CSS code, a X check layer for each X check, join them all together, and that gives you the layer code. And here's this example is Shor's 9-qubit code, written out as a layer code. Here's another example with the Steen code I showed before. This one's a little bit more dense. But again, you can do it. It ends up looking like this. I don't know what it tells you. It's kind of funny. All right, so what are the parameters? So if you plug in a good LDPC code, the claim is you get something that fits in a grid, so it's going to be L cubed. The number of encoded qubits is going to be like, at max you could see it was L. because you started with your L sort of physical qubits on a line and blew them up into surface codes and then added more checks. And the claim is that you keep that scaling. And then to understand the distance, essentially you get the concatenated distance up to some reduction, depending on the stabilizer weight, which I'll talk about in a second, which is that with the concatenated code, you'd have a distance L coming from this sort of good LDPC code on the physical qubits laid out in a line. And then you're going to concatenate those into surface codes, which will also have a distance L, because you're going to have like L by L planes of surface code. And so this gives you L squared. And that's the best you can do, saturating these bounds. Cool. And yeah, like I said before, once you saturate the best distance you can do and the best number of qubits given that distance, you can take this sort of block and make small versions of it and tile to get to saturate this with any kind of trade-off. So I'm going to talk a bit about the parameters in detail. N is pretty easy, the number of physical qubits. The whole thing fits into like this rectangular grid, which is given by the number of qubits of the LDPC code, the number of X checks of the LDPC code, and the number of Z checks on the different axes. And then like you only get at max 2 qubits per edge. So you can even really count this and not just do a scaling, but there's no point really doing that. Okay, so for a good LDPC code, NX and NZ scale like N, and overall, I've relabeled N to be L here. Overall, that gives you this L cube scaling. Hopefully that makes sense. That was the easy one. For K, this is where the main, I guess, proof idea for K and D is this idea of quasi-concatenated logicals, which is that you take some logical. So here is a little picture of like a repetition code on 3 surface code layers with these like ZZ checks implemented by 2 more surface code layers. And on your repetition code, in this basis, you'd have like an XXX logical. Here, you don't quite get the logical of the concatenated code. You get like a slightly different version of it, where you take the concatenated code logical and embed it. But this is going to make some excitations where it like meets these check layers. But because it has to meet each check an even number of times, you can pair these up. And so essentially, you just take this concatenated guy, you pair up its syndromes that it creates along the most straight path using the ordering of everything in 1D. And this gives you a quasi-concatenated logical operator. So essentially, it's like a dressed, no, that's a bad word to use. It's like a logical operator from concatenated code times a bunch of strings to just join everything together. The nice property of these is they give you the same algebra. So because this sort of X quasi-concatenated logical operators only differ on these red layers, and the red ones, which I haven't really done a good example for, but they only involve extra stuff from the blue layers. So if the concatenated logical operators had some commutation, these quasi-concatenated versions have the same commutation. Because the extra bits you put in, they just don't hit each other. So you get a copy of this algebra. So this shows you get at least this many encoded qubits. To see you don't get more, you have to kind of go the other way, which is that if you start from any logical in this code, you can kind of use this sort of topological deformability to squish it into a plane like this. And then once it's in that plane, you essentially can show it has to take the form of a quasi-concatenated logical. And then you can just pull off these extra bits to get back a concatenated logical. And so you know if there was any new logicals in your layer code, you could use them to make up a new logical in the concatenated code, which you assume can't happen. So it's sort of if and only if these logicals with the concatenated logicals. And that's how you see you get exactly the same scaling of the input code. So for a good LDPC code, this is going to scale like the number of layers you've laid out in space. So it's going to give you order L. And then finally, the distance is the most complicated one, maybe not surprisingly. Here again, you essentially use quasi-concatenated logical idea. But so you could see if the quasi-concatenated logicals were all we had to worry about, you'd kind of win because they have weight at least as much as the concatenated logical. And that has a distance that's going to be like L squared for a good LDPC code input. The problem is you now have these new kind of layers where things can wander into them, which were not there in the concatenated code. And so the essential thing you have to do is just bound how much reduction of the distance you can get by this new kind of cleaning of stuff into the layers you've introduced. Oh yeah, and here I've just written out this sort of generic case where you have a more general NX and NZ parameter. So essentially, one of these NX or NZ lengths is going to be shorter, and you get that distance, the minimum of those two will give you like the surface code distance, and then you get this D distance from the input code. And then I'm going to tell you about this 1 over W at the front. So the W here is the stabilizer check weight of the input code. And the reason that you get a multiplicative reduction by that inverse of that check weight is because essentially you can have some, say here, some syndromes kind of wander into one of these checks you've introduced on one of these layers and reduce the weight of the syndrome. Or if you like, this could be part of a bigger logical that was before supported on 2 layers, but now it wanders into this layer and it's supported on 1 layer. And so you can see this is kind of bad. And at first you think, well, can I still get this distance I want? But this is where the assumption that the input code is LDPC is really important. If the input code is LDPC, each of these sort of layers, say these Z check layers, they only talk to a constant number of the data layers. And so if you kind of do a rough worst case thinking, imagine you could get a reduction of up to W from each of these layers because it touches W layers. Imagine all those strings kind of hopped into this new layer and become a single string. Then you need only like D over W of these layers to cover the full logical. And that's kind of the worst case. You can't do worse than that. So that's the intuition for why you get that scaling. So for more general, sorry, there's a bug on me. For more general non-LDPC codes, you might not get this optimal distance, but given the W is a constant, you can achieve this L squared if you put in a good code. Okay. Oh yeah, and then the final thing I want to talk about, which is a nice property these codes end up having, which we kind of didn't aim for at first, but then worked out was there, is that they have this kind of optimal energy barrier given the 3D locality. So the concept of an energy barrier is familiar from like a 2D Ising ferromagnet or 2D repetition code, if you like. And the idea is if you imagine the syndrome has some cost per unit length, and you want to flip this domain of all zeros in 2 dimensions to all ones, you have to basically grow a bubble or a number of bubbles and join them. And this has a boundary, which is the syndrome. And the minimum, highest weight path you can do this with in 2D is to grow this boundary over about half the system. So this energy barrier, which is the scaling of this syndrome, like the peak that the syndrome cost reaches over the minimum of all such paths is going to be at least scaling like L here. And this is kind of my picture of this, a very simplified picture of growing some bubble. As you grow it, the energy of the syndrome cost will increase until some point where you're now shrinking it and you get back to the code space. In reality, there could be a whole bunch of like dips in here. And then what we care about is like this peak and then the minimum over all such paths. Okay. And the idea is this is meant to give you some suppression if you have a thermal cost to your errors, sorry. So if you have some cost where higher energy things are penalized more, hopefully exponentially more, then this will give your memory some robustness if it's just thermalizing at some finite temperature. Okay. So in these in these layer codes, if you input an LDPC code that's good, you can kind of show that the examples we have of these already have an energy barrier that scales like n in the expanded code family. Once you plug them through this layer code construction, you have to worry about like a lot of new stuff that can happen. But luckily, yeah, what you can show is that you only get a constant multiplicative reduction in the energy barrier. So before it was like n, which has become L when you lay everything out in 3D. And so we still get a scaling with L times some constant that's going to reduce the size. And the idea for this proof is pretty similar to the distance. You essentially now consider taking some process that could happen in the layer code, which is going to be a bunch of local excitations hopping around. And they can go into like these other types of layers, so it gets a bit complicated. And then up to some overhead in the energy cost of any of these configurations, you can like back out a configuration that you can interpret as a concatenated logical. And so any path of local hops here, you can back out a path of local hops on the original code up to some like multiplicative constant. And so any energy barrier you had here basically pulls back through to this one, divided by this same constant. And that's how that argument goes. Cool. And so interestingly here, it's really important, this W prime, I didn't say what that was. W is like the degree of the tanagraph of the checks hitting the qubits. W prime is like the degree of the qubits hitting the checks. So that pops up in this. Okay, yeah, so some open questions. I think maybe this work was one that like opened more questions than it answered for sure, for us. And maybe the biggest one, given that I just talked about this energy barrier, is this code has like a really good energy barrier. But also it has like a huge sort of degeneracy of ways of implementing logical operators. So is it in any sense self-correcting if we let it couple to a local thermalizing noise model at some finite temperature that's sufficiently low but constant? Can we get a memory time that increases like exponentially or polynomially with L? Ideally, as we grow L to infinity, but even up to some finite crossover point. That depends on temperature. We don't know. Yeah, how do you decode this? I think that there are some ideas that exist that could be used to decode these codes, but say using the actual structure of surface code plus the code you plug in, how do you design decoders? How do you do gates on these things? And in what sense are two equivalent if the input stabilizer codes are equivalent? These two things are kind of related because this construction really uses the check specifications, whereas we know that the code you put in, you could pick different bases of checks that are equivalent that give you the same code space. Those seem to give different layer codes in what sense are they equivalent. And if you apply a fault-tolerant gate, it might mix up the generating set of checks. So you need to understand this equivalence to understand how to do gates. Yeah, so this construction you can think of as some embedding into 3 dimensions plus weight reduction of an arbitrary CSS code. How about generalizing this to higher dimensions and even no fixed finite spatial dimension, but where you have a bunch of layers and then say totally non-local connections between them. It seems like this construction could give you weight reduction down to 6 based on using these ideas of concatenating with surface code and then some lattice surgery. And then finally, this is related to, I think it's a good question that's been brought up a bit, which is like, say you have some specific architecture in mind that's not just a fixed spatial dimension and maybe different to just like 2D layers with non-local couplings. Can you use layer codes to kind of get optimal codes in that setting? Which I think is a reasonable guess for what to do if your setting involves a bunch of pieces that have to be 2D and then some amount of non-local connections between them. Okay, and me and Noiden will be around, I think, for a while if you want to discuss any open questions about layer codes. So yeah, please come and see us. Thanks.
So I apologize, I don't really understand how this construction works, but do I understand correctly that you, even though you use these line codes, which are good codes, you nevertheless came up with a structure where you have only local checks in 3 dimensions and local checks of weight up to 6. But then the W, the weight for those line codes is pretty big. It's sort of, at least estimates are quite big for those codes. And so then what are the parameters that you expect to get out of this construction? And do you have any examples which are bigger than the steel code?
Yeah, I mean, I guess the recipe you could, as long as you have the tanagraph of the whatever code you want to put in, you have essentially the tanagraph, you just crank the handle and you have the tanagraph of this layer code. It's basically at least as complicated as the code you put in. So if your code example is complicated, this tanagraph is super complicated. And all these results basically live in scaling world. So there's some horrible constants that come in, like these 1 divided by check weight for these good codes. I guess if you want to be optimistic, you could hope that given a bunch of networked 2D codes, you could maybe do better than just sort of taking an already good code and just plugging it in. But currently, yeah, I think we have no way around this. And it seems like these worst case things, they do seem to be able to happen where you can kind of have certain logicals that have like sort of half overlap with a bunch of checks, and then you push them into the check to really get this reduction of W over 2. But I guess you could also hope that worst case scaling is not that relevant. But
And like besides the distance, you also have a very poor rate in general, because if you take even just short code, you're going to end up with like 10 to the cube roughly physical qubits for just one logical qubit, which gives you like 1,000 qubits for one logical qubit. Yeah, they're not very practical at the moment.
Good question. Let's see. Were you able to calculate the entropy as well as the energy?
Yeah, I don't have a formula for that, but that's something we're thinking about. And like the entropy of these like failure configurations I think that would be one way to rule out having self-correction.
Right, or show that it is measurable. And how does this, I mean, if you were to take a very high rate LDPC code in order to lower the number of encoded qubits, it might actually help your argument. But do you know any examples of codes that are like LDPC in terms of their checks that would go into this construction, but which give you like, let's say, one logical qubit to try to simplify the decoder question?
Yeah, no, I don't actually, but that might make things simpler. Because if you just want self-correction, you don't need to self-correct like L qubits, indeed. Yeah, I mean, I should also say in terms of open questions, there's a toy version that's embedded into this, which is like if you concatenate classical code with a bunch of surface codes and then use our weight reduction tricks, you get something that has like kind of good distance against and good energy barrier against one kind of error. And if you could go and check that that works or doesn't work, if it doesn't work, these things definitely won't work. If it does work, it's pretty optimistic that these would work, and that would be a lot easier, I think. Maybe you could just take some like random low degree expander, tripartite expander to define your classical code, and then plug that in and see if that thing's self-correcting.
Any more questions? Maybe one more question. So, I mean, essentially, you use like the optimality of like the surface code, and then kind of leverage this by kind of utilizing like root code. So, if you want to kind of generalize your results to higher dimensions, you can have you have your bootstrap, you have kind of use 3D layer codes, and then kind of.
Yeah, I think actually that's a good question. And at first I was thinking that, but I'm pretty sure that doesn't actually work whatever way I've thought of it. The thing that actually does work is here we have like a codimension 1 kind of line that gets you the K. If you go to high dimensions, take a codimension 2 grid, like say in 4 dimensions, you have a 2D grid or whatever, and then you blow up the extra 2 dimensions as surface codes, and then you have this sort of routing problem. And the reason why the high dimensional version is not in our paper and isn't worked out for our construction is that the routing problem is trivial in 3D because it reduces to like 1D, just joining things up. But once you even go to 4D, you actually have to decide how you're going to network everything, and it becomes complicated. That's good.
If there's no more questions, let's thank Dom again. We have to do a quick break, and then we meet again.